Hello everybody, it's Professor Fiore, and we're going to be looking at capacitors in this video, talking about different kinds that are available, typical applications for them, things of that nature. A lot of new students in electricity, electronics get kind of overwhelmed by all of the different kinds of capacitors there are available. Why so many? Okay, they look different too. Lots of variations on the theme. So here we got a picture of a bunch of different kinds of caps, big ones, small ones, all kinds of weird shapes. What the heck is going on here? Well, besides just the sheer size, the performance of these different capacitors changes. That's going to be a matter of cost and sort of optimization. And we have to kind of pick ultimately the best sort of capacitor for the job at hand. Just to give you a real quick overview of what's out here, because you're going to hear these terms. Right, I'm going to start with some aluminum electrolytic capacitors. Mostly these big monsters, right? So I've got this big one. So this is going to be mounted usually with like a little metal strap or something like that to, a chassis or something. Notice it has screw terminals. Very often you'll find a large value resistor shunting these two. There's a good reason for that, which I'll explain a little later. It has to do with something called dielectric absorption. Some smaller electrolytics we have here, a couple of smaller ones down here, another one over here. So we have what are called axial leads and radial leads. You'll notice in some of these, the leads are coming out of one end, right? And in some, they're coming out of either end. You'll also notice on these that there's a crimp, right? You can see this little crimp over here. And that will indicate a polarity along with a stripe. And also, very often, the length of one of these leads will have been a little bit shorter. Okay, so you can see, for example, here's the stripe and it's right on this shorter of the two leads, right? Because these caps happen to be what are called polarized. They have to be put in the circuit in a certain orientation, right? If you put it in the back orientation, in other words, if you put the plus where the negative part of the power supply is, if it's reversed, if that polarity is reversed, it doesn't have to be a negative voltage with respect to ground. It just has to be negative on these two terminals with respect to each other. If it's, in other words, put in the circuit backwards, this thing can blow up. And modern electrolytics, you'll see at the top, well, what would be up here, you'll often see sort of a little crosshatch, which is a little sort of pressure relief. What will end up happening is these things will overheat, and that pressure release sort of pops open a little bit. It sort of pops up. If it didn't have that, like old style caps didn't have that, this thing would just literally blow up. It'll go off like a firecracker, basically. The guts of this thing will just come flying out. And the guts of this basically is just a large coiled, like aluminum foil kind of affair. And then you have this little rubber stopper in the end. So what will end up happening is this thing will just come flying out, like a streamer, all right? But there are advantages, right? There are advantages to using aluminum electrolytic capacitors. We'll get into it, but I'll just tell you really quick. They have what's known as high volumetric efficiency, and they're cheap, right? They're inexpensive, given the number of farads that you're going to buy, right? Farads per dollar, relatively inexpensive. Other ones that are available, silver mica. These are actually pretty nice caps, stable caps. We've got a variety of different sort of ceramic disc caps here. And ceramic discs, they vary a lot. There are some really, really high quality ceramic disc caps out there, NP0, for example. But then there are others that are very, very sort of sloppy tolerance. Not nearly so nice, very sensitive to temperature changes, right? Tantalum. So we have some tantalum caps here. That's a tantalum cap. That's a tantalum cap. So these are very stable caps. They have very low leakage. Normally, these are also polarized. Other ones that we have some polyfilm caps. So here's a polyfilm cap here. There's another one right here. These are generally very nice quality capacitors. All right. So again, it's going to be one of these things of, well, how much are you willing to spend? How much space do you have? Right? These are factors that are going to come into it because they have different sort of characteristics, different sorts of quality. All right. So what are these characteristics? Well, the first thing I'm going to say is there's a little sort of saying, that I used to use in class, which is, when is a resistor not a resistor? And this is true for a cap or, an inductor. When is a resistor not a resistor? When is a capacitor not a capacitor? When you can hold it in your hand. Huh? What do you mean by that? Well, what I mean is, when a person draws a symbol on a whiteboard, for example, or on a schematic, a symbol for a capacitor, a symbol for a resistor, that really represents a concept. The concept of capacitance or resistance. It's pure, unadulterated, resistor. But the things that we actually hold, the things that we make circuits out of, are physical representations of that concept. In other words, how close can we get to that concept? Because there are going to be non-ideal characteristics in those things. How good can we make it? How close can we make it? So some of those performance characteristics would include things like, well, obviously the capacitance value and its tolerance. Oh, it's a 1 microfarad cap. Great. Is that plus and minus 10%, plus and minus 5%, plus and minus 1%? Right? That kind of thing. A voltage rating. Caps don't have power ratings. They do have voltage ratings, though. Right? You think in terms of the dielectric strength, right? What is the volt rating on that dielectric? So the cap might be rated for 50 volts. It might be rated for 100 volts, 500 volts. That's an issue. Then we have temperature characteristics. What's the range of temperatures under which this can be used, and what sort of temperature sensitivity are we looking at? Some caps are renowned for the fact that they're very, very temperature stable, an NP0 ceramic, for example. Other ones, not so much. Some of the class 2 ceramics that we'll be talking about, lousy temperature sensitivity. They're all over the place. Similar to this, we have something called leakage resistance. And if you took a cap and you charged it up and you just put it on a shelf somewhere where nothing can touch it, and you come back to it sometime later, and that might be days or weeks, that charge will have leaked off. And we can model that as a parallel resistance, right? A leakage resistance. There's also a series resistance, something called an ESR, an equivalent series resistance. And that will limit partly things like the frequency response of the capacitor, the range of frequencies that we can use this over. This is associated with the Q of the capacitor, or something called dissipation factor. If you're looking at a high current power application, that equivalent series resistance has a power dissipation associated with it. So we would like that to be as small as possible. We would like the ESR to be as small as possible. Similarly, there's something called equivalent series inductance. The simple fact that you have a wire lead sticking out of this thing and there's a current flowing through it means there's a magnetic field being created, so there's an equivalent inductance there as well. That will limit the frequency response on the high end. We would, of course, like that to be as small as possible. Dielectric absorption is a characteristic of the dielectric to sort of rebound. And here's what can happen. You could discharge a capacitor, bring it down to 0, and then, after unhooking it from the circuit, right? In other words, there's no more source on it. You would expect it to stay at 0, but if something has high dielectric absorption, it will sort of rebound, almost as if you could sort of mentally think of this as like sponge rubber, like you squeezed it down and then you let go of it and it slowly re-expands. So you could have a dielectric absorption that's 10%. And what that means is if you had a capacitor and it was charged to, let's say, 500 volts, and it's got 10% dielectric absorption, when you discharge this thing down to 0, it can rebound back up to 10% of that 500. In other words, it can rebound back up to 50 volts. Clearly, that could be dangerous, right? I mean, in general circuit work, that might lead to things like distortion, if you had like an audio amplifier or something. But I think, okay, that's not good, but, something that's dangerous, like you're getting this high rebound voltage, that's worse. So that's one reason why you might see a large value resistor across particularly large filter capacitors, for example. It sort of limits that, and it also helps when you turn the power supply off to give a discharge path for that capacitor. Another really important characteristic is called volumetric efficiency. It sounds fancy, but all it really means is how many farads can you pack into a certain size box? Okay? High volumetric efficiency means for a certain amount of capacitance, for 1 microfarad, high volumetric efficiency means the case itself, the capacitor, the thing you're going to solder into a board, is physically smaller. So generally speaking, we would like high volumetric efficiency. But as you can guess, you're not going to get that for free, right? That depends on the dielectric that you're using. Another important characteristic is whether or not a capacitor is polarized versus non-polarized. I've already mentioned that with the electrolytics. So polarized caps have to be thrown into a circuit in a certain orientation. And if you don't do that, if you have them backwards, they will either fail ungracefully or they might explode. Not good. We generally don't like our circuits to explode. And of course, all of these things are rolled together into the cost, right? What does it cost for this cap? Now you might find, 2 competing capacitors that have the same voltage rating, that have the same capacitance rating. One of them is much, much superior, has really low ESR, really low ESL, great temperature stability, and so on and so forth. But, it costs 10 times as much as the other cap. And the question is, well, is it worth that extra cost? No, that depends on the application. Sometimes you just need enough capacitance, and that's all you really care about. It all depends. So I can't give you always use this instead of that. It depends on the application, right? I mean, that's part of the job of being an engineer. Okay, the manufacturers, of course, are going to help you out. They're going to sort of indicate this capacitor or this style of capacitor is designed for this kind of application because it has these particular characteristics, right? It's just up to you to select the right cap for that job, right? So to understand how a lot of these things work together, we need to look at some capacitor models. So here's your idealized capacitor, right? Oh, this is a 1 microfarad capacitor. It's pure, unadulterated capacitance. Great. Here's a better model. I'm not saying this is perfect, but it's a better model. So this would include a parallel leakage resistance that I mentioned, the equivalent series resistance, and the equivalent series inductance. This by itself is a pretty decent model. Now, the values I've thrown in here represent a not very good quality 1 microfarad capacitor. And the reason I've done that is so we can very easily see what these effects are. All right, I want to point these out to you. I mean, more realistically, a quality capacitor of this size, ESR had better be much lower than an ohm, and the same thing for the ESL. It should be way less than a microhenry. And I would expect the leakage resistance to be, megohms, not 100K. But having said that, let's go take a look, okay? Let's see what we get out of here. So here's our basic idealized capacitor, right? 1 microfarad capacitor. Now what I've done is I've hooked up a current source, a fixed current source here, and we're just going to measure the voltage across this thing and plot this across frequency. Now, by doing a Bode plot, we're looking at output over input. The output's a voltage, the input's a current. So voltage over current, hey, that's impedance, right? So we're basically going to generate, kind of a sneaky way, we're going to generate an impedance plot, right? So we can use our capacitive reactance equation, 1 over 2 pi FC, to figure out the capacitive reactance. At 1 hertz, this thing works out to 159 k ohms. And as we go up in frequency, right, we're dividing by a bigger and bigger number, x of c keeps getting smaller and smaller and smaller and smaller. So at 1 kilohertz, this would only be 159 ohms, right? So it just dives like that. So we can see this just by doing a Bode plot, AC transfer characteristic. Let's see, 110, okay, that looks all good. Open that up, looking pretty good. All right, the only thing about this that we have to monkey with is Tina automatically, when you do this plot, gives you the input-output in decibels. So I don't want that. I want this in ordinary units, logarithmic scale. So I'm going to change that, and there we go. So let's get a cursor on here. I'm going to come all the way down here at 1 hertz, And like we said, that should be 159K, and there it is, right, 159K. And then as we go up, if I went up to like 1K, for example, we can see, if I can get on there, that's going to be 159 ohms, and so on and so on. All right, nice straight line. When you plot this on a log graph, you get this nice straight line. That's your idealized capacitor. Goes on forever. Pretty soon at these high frequencies, you can see, hey, we're getting milliohms, micro ohms. We're getting really small values. Okay. All right. That's not realistic. Sorry. Be nice, but it's not realistic. So let's go look at our improved model. So here we include the ESR, the ESL, and the leakage resistance. Again, I will reiterate that a better quality device would have superior component values, right? These would be smaller, this would be a lot bigger. But in any case, if you look at this, you realize this is actually a series resonance circuit. And we can approximate what that resonant frequency is. I'm essentially ignoring the leakage resistance and the fact that this current source has an internal impedance, which is like a gigaohm or something like that. But anyway, we can approximate it by using the resonant frequency of 1 over 2 pi times the square root of LC. You plug this in, and the resonant frequency comes out at 159 kilohertz. And a series resonant, that means that's the dip, right? So the frequency, the impedance versus frequency response is going to kind of come down and then eventually come back up. And that dip, right, that minimum value is going to be whatever the series resistance is, which in this case is approximately equal to the ESR. So, same dealie. We're going to do this little impedance plot by kind of tricking the AC analysis, the Bode plot. And that looks good. All right, so look what we get. This thing dives down. There's our dip, comes back up. We said it was going to be at about 159 kilohertz, and that's exactly what we're getting over here. All right, so again, if I go back to my original, that's a nice perfect straight line, right? From 1 hertz all the way up to 10 megahertz. I come over here, not so much, right? Just so that we can compare the axes here. Let's change that one as well so they're looking the same. Clearly, that is not the same as this, all right? We could also look at the phase, by the way. So, ideally, the phase on this thing would be minus 90. And if you're saying, hey, what about this big jump? Well, look at the scale. It's 89.99 versus 90. And this little thing way, way down here is because of the internal impedance of the source that's here. So, plus, of course, you also have the leakage and so forth. But, ideally, it's minus 90, right across the frequency range. I come over and look at my model, on the other hand, my improved model. Whoa, look at that. So it's 90 out here, right? Minus 90 out here, but then it's actually flipping back toward the positive at really, really low frequencies, and it completely flips over at the high frequencies. Matter of fact, at really, really high frequencies, we're seeing it's coming up to about plus 90. It's actually inductive, which is what we're seeing over here, right? This positive slope up here indicates this is inductive. This is the area that's actually being controlled by the ESL. Holy macaroni, right? I mean, it's a capacitor in this range, but it's actually like an inductor over here. So if you're using this capacitor up here at a couple of megahertz, it's not behaving like a capacitor. All right? It's not behaving like a capacitor. It's actually behaving like an inductor. So, we have to be cognizant of this and choose, in this case, if I'm going to use it, 10 megahertz, choose a better quality cap, a cap that actually works up at those high frequencies. All right, so let's go back and take a look at some of the dielectrics and what we wind up getting out of these, right? I kind of touched on a few of these, but I want to get a little bit more detail on here, right? So I'm going to start off with the aluminum electrolytic. So what are the positives? What are the big things that we would know? Well, probably the most important thing is to understand that it's a polarized cap, right? That's a big limit. There are many applications where polarized caps are a no-no. Don't want to do that. So on the plus side, though, they are inexpensive. Great volumetric efficiency. Get a lot of farads in a small box. You can get very high capacitance values, hundreds of thousands of microfarads. They don't say millifarads. I don't know why that's the case. It's just kind of a weird thing. They always talk about, thousands of microfarads. Go figure. Nonetheless, on the downside, not the most stable. Kind of wide tolerance, high ESR, all right? As I mentioned, high dielectric absorption. That's not so good. High leakage. Possibly dangerous failure mode. I already mentioned this. You put them in the backwards, they can blow up. All right. So where do you use them? What kind of applications do we have? A standard like analog non-switching power supply. I need a power supply filter after a rectifier. That's a great application. Power supply bypass, like in an audio amplifier. You will sometimes see these in parallel with a small film capacitor. Right? Some people would call that a helper capacitor. I'll explain exactly how that works momentarily. We might use it for signal coupling, for example. Again, I'll just throw it out there for like an audio amplifier. Interstage coupling, if it's not direct coupled, we might have something like that because I might need a fairly large value depending on what I'm coupling to. So that's the deal there. For the aluminum electrolytics, you're largely thinking in terms of lots of farads. I need a lot of farads. That's probably what I'm going to run to. If I can tolerate a polarized thing and, all those other limitations. Kind of the exact opposite of that is a class 1 ceramic, an NP0 or a C0G. These are non-polarized. These are actually really nice capacitors. Low ESR, low ESL. Like I said, high stability, temperature requirement, very, very nice. What's the downside? I mean, if that's so great, what's the downside? Well, you can't get very large values. I mean, tens of picofarads, hundreds of picofarads, maybe low nanofarads. You're not going to find a class 1 ceramic that's, 470 microfarads. All right? So you can't, right? You can't. I mean, even if you wanted to, you're not going to find them. Okay? So where would we use them? Well, any place where we need very tight tolerances, high stability. All right? So I would be thinking something like filter circuits, timing circuits. Because of the low ESR, this would be good for power applications like pulse kinds of circuits, high power pulse circuits. Maybe like a switching power supply kind of application, something like that. Another class of ceramics is the class 2 ceramics. These are much, much looser. They're nothing like these class 1 ceramics. Plus side, high voltage rating. They are relatively inexpensive, depending on which kind you get. And the weird thing about this, there's a lot of these. And the X, the 5, the R, in other words, the first letter, the number, and the second letter, indicate things like the absolute tolerance and the temperature sensitivity. Right? I'm not going to go through like all of the possibilities, but some of these things are amazingly bad. In other words, we're talking tolerances of maybe minus 50% plus 100%. In other words, you can get 2-to-1 variations based on the nominal, right? So the thing says X farads, but you could have twice that or half that. Okay, they vary all over the place with temperature. Another problem is they can be microphonic, meaning they can actually pick up physical sensations. Right? And that would like modulate the capacitance. That can be a problem in certain kinds of circuits. So they're not really all that great. Where would you use them? Well, basically you use them where, you don't need a particularly accurate value of capacitance. I just need enough capacitance. So something like, a power supply bypass, you might use it in there, maybe with other caps, possibly signal coupling. All depends on sort of the frequency range that you're working in and what the impedances are. All right. The important thing to really remember is that a class 2 ceramic is nothing like a class 1 ceramic. So if someone says, you need a ceramic here, and they don't specify, look into it. If it's a particularly small value, if it's like a 47 picofarad ceramic, chances are they probably wanted you to use something like an NP0, right? Little side note here, if you're talking to an old timer, right, someone who's been doing this for a long time, who learned this back in the 60s or 70s, they might pronounce picofarad, PF, as puff. So they might say, well, you need a 47 puff cap in there. That's what you need, 47 puff. So that's what they're talking about, right? Puff, picofarad. All right. They may not have a stupid accent like that, but whatever. That's my old guy accent. Anyway, moving along. Tantalum. So these usually look like sort of like a little blob with a couple leads sticking out of it. These are very stable capacitors, very high leakage resistance, meaning they have low leakage. All right. They're much nicer than the aluminum electrolytics. They are, however, polarized like the electrolytics. Again, possibly dangerous failure mode. You put them in backwards, they can explode. All right, not so good. Classic example use of these is power supply bypass. All right, so you'll see these, like in digital circuits or something, right at the power supply pin, you'll see a little tantalum capacitor. Okay, moving along, film capacitors, and there's a ton of different kinds of film capacitors. We've got polyester, also known as PET, or mylar. Mylar is a trade name. Polypropylene, Teflon, another trade name, polyethylene, polyphenylene. Generally speaking, film caps are nice. They have low ESR and ESL values, low dielectric absorption. They usually have pretty tight tolerance, good stability. They can be self-healing, which basically means that if you put an overvoltage on them, once it's removed, the dielectric, the way the thing is constructed, it can actually kind of fix itself in a way. So that's kind of a nice thing. Some of the other specifics, like the volumetric efficiency and how much they cost, will depend on the kind of film that you have, what the dielectric is. But generally speaking, these are, like I said, good quality capacitors. So for a general purpose application, film caps are usually a nice thing. So I would think in terms of, like, let's say, an audio filter, like an active filter or a coupling thing like that. Those are usually pretty good choices. All right. In the audio world, polypropylene capacitors have a really good reputation. The problem with polypropylene is they're physically large. They don't have very good volumetric efficiency, and they're pretty expensive by like an order of magnitude compared to maybe a polyester. So polyester is kind of like a first run. It's like that's the first one that people run to when they need a film cap because they're widely available, lots of different sizes. They work pretty well, but then, depending on the application, you might want something that's a little bit tighter, a little bit more stable, and you'll look at some of these other ones. All right. Teflon caps are another really high quality capacitor. Not nearly as common though. What are you going to do? If you look at some older designs, you'll see some other kinds of films, polycarbonate and polystyrene. These are actually pretty nice caps, but for the most part, they don't make them anymore. The application areas weren't that great, where they really sort of stood out. So the manufacturers have kind of abandoned them. And now you just look for other kinds of films, polyfilms. All right. Coming down to the next one, silver mica. These are very stable, nice, very nice capacitors. They can be expensive. And in some areas, they are being replaced by the ceramic class 1s. All right. Okay. Last one on my list is an air capacitor. So we use dielectric. The dielectric is air. What? These are usually pretty small. 100 picofarads to 1 nanofarad would be typical, and we would use these as tuning capacitors. Back in the old days, zoink, that is an air dielectric tuning capacitor. This is what we used to use in days gone by to tune a radio. All right, this is actually 2 capacitors. There's one here and there's one here. Notice what's happening. You've got a bunch of plates over here, and then there's a bunch of plates down here. So these plates are fixed. These plates, they're attached to the shaft. So as you rotate the shaft, this set of plates intersects more or less this set of plates. And of course, the more overlap you have, the greater the capacitance. So as you rotate this, you have an adjustable capacitance. Kind of like a rheostat, but it's a capacitance. All right, this has 2 of them. So you don't need a lot of capacitance, but that's what we used to use, before we had things like varactor diodes to do it electronically. And we do it mechanically. All right. Okay, fun little thing. All right, so lastly, I thought I would just throw out a little data sheet here for capacitor. What kind of things would you see? All right, so in this particular case, here we have the capacitance values, because there's a couple things I want to point out here besides the obvious, which is the physical dimensions are getting bigger as the capacitance grows. That shouldn't be surprising. Same thing would be true with the voltage rating, right? You get a bigger physical size as the voltage goes up. But I wanted to point out some of the values here. All right, so we've got an ESR. This is measured at 10 kilohertz. Notice this is in milliohms. And we're looking at 13, 9.5, 7, right? Much, much smaller than the little model that I used. All right, this is much higher quality. But notice, and this is important, notice that as the capacitance goes up, the ESR goes down. Right? That's good. It's kind of expected if you think about it. You got a greater plate area, so the resistance associated with that goes down. We see a similar kind of effect, as far as it getting better for you, is the ESL, the inductance, only measured in nanohenries, right? We see this changing again in accordance with the capacitance that we have, okay? Now, this over here, this is another way, this sort of tan delta thing over here. This is the dissipation factor, which is another way of computing. This is very commonly done in power applications. It's another way of considering what the ESR is, okay? But I want to bring your attention over here to these graphs. Take a look at this graph, right? This is the impedance versus frequency. And what do we see, right? There's 4 different cap values here, but we see it back here dropping like we saw. We get the dip, and it pops back up, right? This is the exact thing that we saw with our model. All right, and the smaller the capacitance is, the higher up this curve is, which would make sense. Okay, but it also goes out to a higher frequency, right? It behaves as a cap, ideally, to a higher frequency. All right, so but there's that dip, right? And that, like I said, that dip kind of indicates to you what the ESR is. And the ESR is not a fixed value; it actually varies with frequency. So we can see it's a little bit bigger here at these lower frequencies. Right? These are still pretty small numbers, right? This is still measured out in milliohms. But we get up to a certain value. We get up in the kilohertz and higher. This pretty much flattens out. Okay? All right, great. So, ultimately we have to come back to the fact that our real-world capacitor looks more like this rather than this. Right? And we have lots of options. We have lots of different dielectrics. And those dielectrics skew towards certain kinds of applications. There are pluses, there are minuses. All of those things have to be considered. And that is ultimately, part of the job of being an engineer is knowing what to use where. You want to get the most out of this, okay? Highest reliability, lowest cost, whatever it happens to be, okay? Best possible performance you could possibly get. Maybe that's what you're after. All right, well, I hope this has answered a bunch of your questions about capacitors, the different kinds, where they're used, and so forth. This is Professor Fiore saying, take care, and I'll see you next time.